Okay, welcome to Mr. Dahlstrom's Pre-AP Physics 2020 projectile motion, and which is part of two-dimensional motion. This is an introduction to projectile motion. I'll be limiting a little bit of the conceptual stuff and concentrating more on the mathematical and the problem-solving component of it today. There'll be future videos over the conceptual will come later. So the biggest thing, or I guess a couple things about this is two-dimensional motion. We just got done with vectors, so being able to split up some vector at some specific angle into its x and y components. And then also, once we have the components, we use the Pythagorean theorem to figure out the magnitude, and we use the inverse tangent to find whatever that angle happened to be. So a couple things about projectile motion, or motion in two dimensions under what we call projectile motion. In the x direction here, let me adjust my light here. In the x direction, it is constant velocity, as we see here. There's no acceleration horizontally. We're assuming that there's no air resistance, or that the air resistance is negligible, where it does not have any effect on this. We saw this in free fall, that we can basically model falling objects or objects moving up and down with no air resistance if we basically make it so that the mass is either big enough or the surface area is small enough that there's no effect. So once again, the free fall equations we can only use are with no air resistance there. So in the x direction, we only have constant velocity, so we have Vx, which is delta x over t, so displacement over time. And I want to point something out here. The reason why, we'll go over later, for example, in free fall we have Viy and Vfy. The reason why we only have Vx here and why we don't have Vix and Vfx is, if you think about it, the moment, and this is a little conceptual here, the moment that anything is, let's just say that there's something that's being pushed off the side and it's falling down like that. If there's no acceleration in the x direction, the component of this, so the Vx is V cosine theta, so if there's some velocity here, the component of that in the x direction has no acceleration, and the beginning velocity would be exactly equal to the final velocity, remember, just horizontally. So instead of saying that, we just write Vx instead. So it means for that. So we don't have to differentiate between initial and final, because there is no difference between initial and final. It is always the same, always the same, the whole entire problem. For the y direction, so once again, maybe I'll put it here, no air resistance either. It's not like we have air resistance in one direction and not the other. So we'll never do air resistance in my class pre-AP Physics, so at least not under the current standards. The y direction, basically we go back over the free fall rules. This is why learning free fall was so crucial and making sure that we mastered that, because now we're basically going back to it again. So the only acceleration is, sometimes I put arrows and it gets confusing. The only acceleration is gravity, or the acceleration due to gravity, which we've always used as negative 9.81 meters per second squared. And we have over here, we have our free fall equations. These are the same order of ones that we had when we were in free fall. Remember, reminding over here, we write off to the side what each of these don't have. This one doesn't have gravity. This one doesn't have delta y. This one doesn't have Vfy. Sorry if you can read that, Vfy. And then this one doesn't have time. So we used a specific strategy in my classes that was called the 4-2 strat, or the 4-2 strategy, when we didn't have final velocity and time. We will also be using that strategy because it's very helpful in doing this, in order to avoid the quadratic equation. So, using the third and the quadratic. Okay, so how we're going to set up all of our problems, you're going to use this T-chart, and it's extremely important that we use this T-chart to organize our work. Just to give you proof here, I've been working through the AP Physics problem so I can provide some extra help to the students, and so let me show you every example of when I've used this. So here's an example. There's the X and Y chart. Let's go through all the other ones I have here. This one has a lot. There's one there. That problem didn't have it. There's one right there, so I set it up. Next page is a lot. There's one there. There's one there. There's one there, and there's one right there. So every single problem that I'm doing AP-wise, or even a little bit more complex, I always start this out with this. So make sure, so you're following along with what we're doing in class, that you are also writing it in this order. And I just do it in order of, no, it doesn't really matter there, but I try to line up the velocities, the displacements, the time, and the gravity, and then VFY. So key facts. This is what makes this whole problem, being able to solve something in the x direction, or it's a y direction, x direction at the same time, is that time is the same in every direction, and that is our key. That is our portal from understanding the x direction, the y direction. Because if something goes up and then goes down, the same amount of time it's in the air is the same amount of time it's moving sideways. So that is really, really crucial there. So this is going to be our setup for every single problem that we do. So I'm going to move here to a worksheet that we're doing in class. Or before I do that, sorry. Let's talk about the 3 types of problems. You can basically classify every type of projectile motion problem into 3 different types, and this is the order that we're going to do. The first type is what I'm calling horizontally launched. And in horizontally launched ones, it's at some height, and it's launched at an angle, so it has some velocity at an angle of 0 degrees. So it's going to fall like this, okay? That's the first type. That's what we're going to be looking at today. The second type is, there's a couple different ways that this can be. This is the most diverse of ways that you could solve this one here. So you can have it going, at an angle here, up and then down. You could have it going, you could have it be here and then it's actually face down here and then has an arc. You could have something where it's here and then going up and down. You could have something where it's maybe there's a problem that we do where there's like a tree house or something, and the object is being shot up towards that. So those are all, sorry I was off screen. Those are all ones. We're going up, we're going down, or in this case, so very diverse. This may look more complicated because there's more situations, but believe it or not, the same exact way we're going to solve this is the same way we're going to solve this. The only difference between these two, the only inherent difference, is that this delta y for these is always going to be negative because you can't shoot something sideways and have it go up. So it's that, yeah. So the delta y here, the delta y would be negative, negative number. Delta y would be negative number. Delta y would be positive number because it's displacing itself upwards. Delta y would be positive here. So whereas in here, the delta y would be just negative. But I don't want you to necessarily memorize the cookie cutter. We're going to be able to analyze any problem. So in the past, I taught these like as 2 completely separate problems until I was like, wait a second, you can solve them exactly the same. And I knew that, but for some reason I had always separated them, probably because regular physics and basically standard physics, this is the most complicated problem that they do, and this is a problem that we didn't used to do until we started putting it into pre-AP physics, and now it's going to be as easy as the other ones. The third one is just, so we'll call this, we usually call this angled launch. Let me move my camera here, sorry about that. Angled launch uneven ground. So you'll know what you'll mean when I mean there. You'll see what I mean there in a second. Uneven ground. This just means you have some delta y that is either positive or negative. In the last scenario here, we have, this is what's called angled launch even ground, meaning that it is going to start and stop. It's going to begin and end at the same exact height. So this would be like, kicking a soccer ball up. It's going to have some velocity there. It's going to go up, and then it's going to come back down. You solve this problem the same every single time. It's different. We're going to approach it a different strategy. We're still going to use this setup here, but we're going to kind of treat it differently. Basically, we're going to figure out what's the time it takes to go there, double the time, and then figure out the total distance. So that's basically the same every single time. So we're going to look at horizontal here, and so really, once again, you'd solve this the same exact way as you would the second type. So we'll transition over here. Okay, so we're going to do just the first one here. Actually, maybe we'll do two here. But horizontally launched projectiles practice homework. Okay, we'll read through the problem. We'll draw a picture. Drawing a picture is extremely important because it lets you figure out what's going what. Because sometimes the description may not give you all the facts. Without the picture telling you more. In her physics lab, Hazel whirls a 10-gram marble down a ramp and off the table with a velocity of 1.2 meters per second at an angle of 0 degrees. Remember that angle is always measured compared to the unit circle here. So when we say 0 degrees, we mean to the right. 0 degrees there. The marble falls in a cup placed 0.51 meters from the table's edge. A, how high is the table, or I guess more specifically, what is delta y? If you find delta y, that's totally fine for me because the delta y here is going to be negative. But how high is the table? What was the velocity, magnitude, and direction of the marble when it hit the ground? So this is something new I've added in here. This may seem more complicated, but this is all you're doing is you're doing Pythagorean theorem, which we did for vectors, and the inverse tangent, which... well, I'll go over when we get to that problem. But that's something my students in my class can do with their eyes closed because they proved it on the quizzes. So let's draw a picture here. It doesn't matter where we draw the picture. I'll draw it off to here just to give me more room over there. So it's talking about basically a table. It does describe a ramp here, but the ramp isn't important because it's telling us the velocity at the very end of the table here. So it's telling us the velocity there. It's saying that it's the velocity is 1.2 meters per second, and the angle is 0 degrees. And what it's also telling us is that it falls into a cup. So there's a cup somewhere out here. This is actually a version of a lab that AP Physics does, where they have to calculate where the cup is and do trials that hits there. So it's going to travel in a parabolic arc here into the cup. So that 0.51, we label here, this is delta y, and this would be delta x. They're telling us here that 0.51 is this right here, okay? And we don't know delta y, that's what we're trying to solve for. There is a piece of information in here that is not needed. This is the 10-gram marble here. We have no air resistance, and we'll see in future videos here that if there's no air resistance or there's nothing affecting its motion, that it doesn't matter if it's a 10-gram marble or a 1,000-pound elephant or whatever like that. It's going to fly through the air with the same with the same motion for that. So it doesn't matter. All things are acting just under gravity. Okay. So let's go ahead and set up our chart over here. So x direction, y direction. Vx equals delta x equals time equals VIY. You can see I'm very fast to be able to write this because I've done it a million times with my AP problem solve. Time, gravity, and VFY. And one thing I forgot to mention here is that we're always going to know what this is. That's the nice thing about free falls, that we always know what the acceleration is, so we don't have to solve for that. And so we're going to go ahead and look at our picture and look at this, what we have. Before we plug anything else in here, the first step comes from vectors. We want to figure out the components. So find the velocity components. Okay. Now, when we did that when we were doing vectors and vector addition, we were using cosine theta and sine theta for this. So Vx would be V cosine theta. VIY would be V sine theta. Usually when I'm solving, I'll put that off of here to give you more room. But that is, in this case, 1.2 cosine 0, which, big surprise, is a 1.2. And 1.2 sine of 0 is 0. Now you may be saying, that seems kind of excessive to do that. I could have just told you that it's going to the right at 1.2. Yes, but remember, we are eventually going to have problems where there is going to be an angle here, and you're going to have to figure out how it's moving up and down and side to side. So even though this is 0 degrees, it's very, very good practice because you're going to have to calculate that each time. So when we do that, we'll go over here and we'll fill in what we have here. So 1.2 meters per second and 0 meters per second. We can also look at the table and realize that we have the delta x here, which is how far it's moving away from the table. Okay. Now, what I like about using this table here and these problems, if we think about it like this, is that there'll either be enough information in the x direction or there'll be enough information in the y direction for us to solve. The key to finding, the really key to finding this, and that's why I said the key fact here is that the time is the same in both directions, is that, for example, if they don't give us enough information in the y direction, we can't use any of our equations to solve. There will be enough information in this direction to find the time, or at least it may give us the time, and that time is the same over here. Or it may not give us enough information in the x direction, but there'll be enough information over here to find the time to plug it in over here to solve this side. So basically, this is sort of the portal between here. Either there'll be enough information over here and plug it over there, or there'll be enough information over here and then use it to plug over there. Okay. I mean, the Foley, even though it doesn't ask us this, it's good practice to try to solve for each of these, because if you can solve for all of those, you can do basically a lot of the AP level problems that we're doing. They're just longer. They're not more difficult. Not most of them. All right, so if we look at here and say, well, do we have enough information in the y direction here? If we look at our equations over here, okay, we don't have delta y, we don't have time, we don't have VFY. So if we're trying to find delta y here, we can't use this one because we don't know what VFY is and we don't know what time. We can't use this one because we don't know what VIY is, or sorry, we don't know what the time is. And we can't use this one here because we don't know what VFY is, and yeah, for that. So we can't solve this. There's no way we can solve this. So what do we I always joke, would we just go ball up and cry ourselves to sleep? No, we look at the other direction. Yes, there is enough here. There are 3 variables. We know 2 of the 3, and we can solve for that. So we're going to use that. And I always like to kind of mark out my work here and saying, okay, I am dealing in the x direction. All my work underneath this here is the x direction. So my equation, which is really nice because there's only one, is Vx is delta x over t. Vx is 1.2. Delta x is 0.51, as was stated over here. And we solve for time. Multiply time over, divide by 1.2. Time is 0.51 divided by 1.2. I already solved this, but I'll go ahead and do this. 0.51 divided by 1.2 comes out to 0.425. I usually round out to 2 decimal places here, so I'll just go ahead and do that to keep it consistent here. Okay, so that is our time. And so I didn't really accomplish anything. It's a necessary thing you have to solve for because we now know. I'll go ahead and I'll write it in a different marker. This is what we just figured out here. So 0.43, and we now know that that's 0.43, which is very helpful because now that we have the time, if we go back to our equations over here, okay, we can't use the first because we don't know what the final velocity is. We could solve for it, but if we look kind of through the equations here, we don't necessarily have to solve for it for this one. We could use the third equation right here. Okay, so I'm going to go ahead and use the third equation. So this is now the y direction. I'll try to split it off here. And the third equation, or at least the third equation that we call in my class, is this equation. Usually we've avoided this one because if we didn't know the time, we'd have to do a quadratic, but we know the time, and that's what makes it better now. So delta y, VIY is 0. I'll just put the time there. That's going to cancel out because VIY is 0. Plus 1/2 negative 9.81 times 0.43 squared. So if we calculate that, we get negative 0.91 meters. And so it asks, that's what delta y is. It asks what the height is. I mean, I would accept either of these. If you wanted to rewrite it to say that the height was 0.91 meters, you could do that as well. But both of those I would accept as the answer. Okay, so finding that. So this one was relatively more easy because we didn't have to find the time here. We could just use this one equation and find the time. And so we have that. Now I've added this question here, what is the velocity, magnitude, direction of the marble when it hits the ground? What this is asking here is that so this is part A, if you want to go ahead, and that's part A right there. If we want to conceptually kind of understand what's happening here, when it hits the ground, it's going to be going at a specific direction. And so if we think back to vectors here, this has we can split this, so I'm going to draw this a little bit longer here. We can split this in terms of how far or how fast this thing is moving sideways, and then how fast this thing is moving down. And if we use the Pythagorean theorem, if we know the two sides here, we can find this. This is the velocity, this is Vx, and this is Vfy. And if we can use the Pythagorean theorem. Now, we need to solve for this. So we found that this is negative 0.91. That's something we just solved for. Okay, I'll just 0.91. So in order to solve this, we do have to solve for final velocity. And if we look back at our equations here, look at our equation. Really, we can use any equation that has final velocity in it because we have everything else. We saw that in free fall. The more information you have, the better you can use. Most people choose to use the second equation here because once you have the time and once you have the initial velocity, it's pretty quick. So I'm going to go ahead and use that second equation to find that. So Vfy equals Viy plus gt. Sorry, I went a little bit long there. Vfy, Viy is 0, negative 9.81. And this is 0.43. Apologies, running off the table there. Vfy is negative 9.81 times 0.43, negative 4.22, which makes sense because it's going down when it's hitting the ground here, okay? So negative. So in order to see this here, we basically have a triangle where this is V, okay? This is Vx, and this is Vfy. We just found Vfy, so what's the question is, what's Vx? And remember, we solved this in the very beginning. This is Vx. This is what I talked about. This is why on the notes, if I go back here, we didn't have a Vix or Vfx because it's the same every single time. So in order to find our magnitude here, the Pythagorean theorem, this is 1.2 because that's how fast it's going sideways the moment it hits the ground. And this is negative 4.22 because that's how fast it's going this way. Okay, so we're going to do the Pythagorean theorem real quick. This is something that's kind of everybody in my class should be bored to death by doing by now. Remember that in your calculator, make sure you put parentheses before you square it because your calculator will take a negative number, like negative 10 squared, and give you negative 100 because it thinks you mean 10 squared times negative. Master tip, just when you're doing this, if you know this is supposed to be a negative number, just do 4.22 squared. But 1.2 squared plus 4.22 squared. Take the square root of that number, and we get 4.39. Okay, that's my magnitude. That's what this is right there, meters per second. There's the magnitude. And to find the angle, I know I kind of ran out of room. I did a space here, but I'll go down here. Sorry. To find the angle. Sorry, there ran out of room. To find the angle, we use just to show you, inverse tangent of the velocity in the y direction, which in this case over velocity in the x direction. It's based on the right triangle. So it is the inverse tangent of what we just found, the negative 4.22, which is that, and 1.2. This should be in a specific quadrant here. Should be to the right and down, which means it should be in the fourth quadrant. So when we put this into our calculator, this may seem excessive, but if you remember, this is what we did this for like 2 weeks. So inverse tangent of negative 4.22 divided by 1.2, and it's negative 74.13 degrees. Now, in my class, we don't use negative numbers, and so if this is the prediction we have, the calculator is telling us it's in that quadrant there, and whenever they're both in that fourth quadrant, we add 360 degrees to this. Answer plus 360, and we get 285.87. That is our angle. So, seems like a long problem. Realize this last part, this last part of the problem, basically everything that's right there is what we've been doing for the last 2 weeks. We just had a quiz where like the average was like a 99%. So this is something we just have to introduce that. So if we go back actually to how to solve the projectile motion, this should be review. If we go back up to here, the first thing we did was we find the velocity components. Okay, there. Second thing we do is we set up our table, plug in as much as we have. We figure out which direction we have enough information in. In this case, we had the x direction. We solve for the time to find that, and then we plug that time into this time because it's the same, and we solve for delta y. Then, to find the magnitude angle, we had to find the final velocity. We then plugged that and that into the Pythagorean theorem, find the magnitude, inverse tangent, angle correction, 285.87 degrees. So I probably in the future, I'll just always do these like somewhere up here just to give myself a little bit more room associated with that. So let me see here. Sorry, check my papers real quick here. Yeah, okay. So that, I don't want to, this is a really long video, it's already 27 minutes, so you obviously go through there. I'm going to create some shorter videos that are going to go over some other ones that we have here and some conceptual. I just wanted to walk through what we're doing, how to basically set up a problem, and then solving that problem. So I'm going to go ahead and sign off here, or I'm going to log out the video here, but I will put this up on Schoology, so this worksheet will be up on Schoology for those of you that are at-home learners. So have a good day. This is Mr. Dahlstrom signing off.